Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Alhamdulillah rabbil alamin. Wassalamu ala sayyidina Muhammad wa ala alihi washabbihi ajmain. Rabbi shrah li sadri wa yassir li amri wa laqnatan min lisani yafqahu qawli. Rabbi zidna ilma warzuqna fahma. Allahumma faqina fidan tawil. Okay, alright, welcome back to fluid mechanics class. Inshallah, today we will continue with chapter on finite control value analysis, chapter 3.3. We'll be looking at Bernoulli equation application and momentum equation. Alright, this chapter we will be looking at Pitot tube. Okay, Pitot tube is part of Bernoulli application equipment, and we will be looking at momentum equation. Okay, what is Pitot tube? Pitot tube is a device that can be used to measure the pressure at stagnation point 2, which is in this figure lah. Okay, this type of tube here, the L-shaped tube, we call it Pitot tube. Okay, at the front of the tube here, at point 2, okay, the stagnation point, the velocity is equal to 0. So here we have a pipe, okay, and inside a pipe we insert a Pitot tube looking like this. Okay, Pitot tube, okay. At the point at front of the tube we call point 2 here, and then we have another one here, this piezometer, which is point 1. Okay, okay, the velocity here at point 2 is equal to 0. Okay, the tube here is the Pitot tube. Okay, let's look at an example of the Bernoulli device application. Okay, for example, we have here velocity measurement by a Pitot tube, Pitot static tube. Okay, a piezometer and Pitot tube are tapered into a horizontal water pipe as shown in the figure to measure the static and stagnation, static and dynamic pressure. 4 indicate water column height, determine the velocity at the center of the pipe. So here we have a pipe, water flowing in the pipe, and here we have a straight tube. The straight tube is a piezometer. It's used to measure the dynamic pressure. And we have another one, a Pitot tube here, the L-shaped tube, a Pitot tube, to measure the pressure at stagnation point, or to measure the static pressure. Okay, the velocity here at point 2 is equal to 0 also. So we have the column height. Okay, column height from point 1 to here, point 2 here, point 1 to the water level here is about 10 meter, and then we have the column height from point 2 to the water level here on the Pitot tube is about 22 centimeter. Okay, we want to find the velocity here, v1. So how we find velocity? Very easy. So we have here water flowing. The water flowing here. Okay, we want to find the velocity v1. Okay, they given us the column height. So the column height from here to here is 10 centimeter, and from here to here is 22 centimeter. So since the problem is involving the Pitot tube, so Pitot tube is a part of Bernoulli application, so Bernoulli equation application. So we are using Bernoulli equation to solve this problem. So what is Bernoulli equation? We have P1 over gamma plus V1 square over 2G plus Z1 equal to P2 over gamma plus V2 square over 2G plus Z2. Okay, since the elevation of Z1 and Z2 is the same, so we can cancel out 0, 0. So velocity at point 2 is equal to 0, so here is 0. So we now have P1, P2, and we have V1. So we want to find the V1, what is the value of V1? So first we need to find the value of the pressure at point 1 and point 2. So how we find the value of pressure at point 1 and point 2? We can find it using P1 equal to rho G H1 and P2 equal to rho G H2, and then we can solve this equation. Okay, we already have the H. H1 is equal to 0.1 meter, while H2 is equal to 0.22 meter. 0.22 meter. Okay, using these numbers here, just substitute the values inside this equation P1 and P2, and then we can find the value of P1 and the value of P2. And then we can also we already know that gamma is equal to rho G. Okay, the rho of water is 1000 times by 9.81, so we got 9810 lah. Okay, 9810 for gamma, the value of gamma. Okay, alright, so then just substitute the value and then you can find the V1, the value of V1. It's very easy, eh? Now let's continue our chapter on the. Okay, this is how you solve the problems. I already shown it to you. Okay, so if you have any inquiries, just can refer back the slide I will be giving to you. Okay. Alright, so next we'll be looking at the linear momentum equation, which is the second law of the momentum equation. The second law of Newton law. Okay, the sum of the total force is equal to the mass times acceleration. Okay, what is the momentum? So momentum is just very simple. Momentum. So let's say M is momentum. The sum of mass times velocity lah. Mass time acceleration. Okay, mass time acceleration. So mass time acceleration. So acceleration is V over time, or can is as can write it as ma lah, acceleration. Okay. Or you can also we can as described in Newton's second law, momentum is the mass time acceleration, but can also be referred as momentum, the rate of the rate of change of momentum. Okay, rate of change of momentum. Alright. So the linear momentum is a product of mass and velocity, and its direction is the direction of velocity. Okay, for example, we have here mass is moving to the right with a velocity v. Okay, so the momentum of the mass here is m times v vector. Okay, the net force is equal to mass times acceleration, or we can also write it as a mass time rate of change of momentum. Okay, Newton's second law is also expressed as the rate of change of momentum of a body equal to the net force acting on it. Okay, alright. So let's look at example here. Okay, we have the sum of total force is equal to the mass acceleration. Okay, alright. So we have here this figure here. We have a pipe. We have a pipe with a small exit. Small exit here. So now we have a pipe. We have a pipe here with a small exit. Okay. For example, we have here 0.1 and here 0.2. Okay. In order for the pipe to be stationary or static, the pipe is require an anchoring force. Okay. We require an anchoring force. Okay. So anchoring force is a must. It's a must. So in order the pipe to be static, or we have here the anchoring force Rz in Z direction, anchoring force Fr in X direction. Okay, we have anchoring force. And then we have force from the water. So water flowing in the pipe, here, they're giving with a pressure 1, the water flowing at pressure 1. So the force that applied, the pipe here is our the pipe here is our control volume here. The pipe here is our control volume. Okay, control volume, please refer back the notes I given you before, the lecture I given before is control volume. Okay, the pipe here is control volume. The volume, the volume area that we consider, we study lah. Okay, control volume, the area that we study. And we only study inside the control volume here. So the pressure here, we have pressure 1. So the force here is equal to F1 equal to P1 times A1 lah. Okay. Alright, so we have here force. And then the water here from the pipe exit to this small area here, small section area here, which is a PATM lah. So the water is diffused to PATM, okay, to the atmosphere. It's diffused to the atmosphere here, PATM. Okay. Alright. So since we study the control volume here, so you must remember that the pressure, okay, the force is applied to the control volume. So PATM here we have a force 2 equal to P2 A2, which is P2 is PATM lah. Okay, P2 is PATM. So the force is applied to the control volume. So we have here P1 lah. F1 P1 is applied to the control volume V here, CV here, and we have PATM here applied. The force from the PATM applied to the control volume here. Okay, alright. So we have there. And then as we have, okay, to solve this kind of problem, so you need to list the total force in S direction, list total force in Y direction. Okay, we need to list the total force is X and Y direction. Why we listing the total force in X and Y direction? Because here we have an angle of 30 degree, right angle of 30 degree. And here we also have the elevation V, elevation Z. Okay. So alright, so we have two component force in X and Y direction. Okay, force in X and Y direction. So what the force in X direction? Okay, force in X direction. First we have the anchoring force, FRX. So we have FRX. Okay, since we consider moving to the right is positive, so we have another one force, F1, moving to the right, so plus F1. Okay, and we have another force which is F2, but F2 is with angle of 30 degree, so we want to find the force in X direction only. So F2 cos 30 lah. Okay, but the force is moving against the direction of the water. Okay, against the direction of water, moving to the left, so minus F2 cos 30 degree equal to, okay, we know that the total force, we have here total force is equal to F equal to MA, or equal to M over V over T, or equal to M over T times V. Okay, and M over T is equal to M dot. This is the mass flow rate. Okay, so we can write it as M dot equal to V. So here we have V. So V1, we have here V1, and we have here V2. V2, same here, cos 30 minus V1. Okay, because the equation of the linear moment equation is just a simple equation, total force equal to, okay, mass flow rate times volume velocity 1 minus velocity 2 in bracket. Okay, so this is the force in X direction. So next we looking at the force in Y direction. So in Y direction, considering the moving upward is positive. So we have what kind of force we have? We have FRZ. Okay, and then what else we have? We have plus or minus. We have minus. So moving upward is positive. Here we have F2 here. F2 here is going from the sign here and Y direction. Direction moving downward. So minus F2. So what is F2? So F2 in Y direction equal to F2 sine 30. Okay, equal to M dot times. So we have V2. V2 is as in Y. So we have here. We have here V2. V2 in Y direction is moving downward. So minus V2. Sorry, this is not minus. Sorry, not minus. Yes, V2 minus V1. But since there is no V1 in X direction, here we have no V1 in Y direction, only in X direction. So V1 in Y direction is equal to 0. So we have here the total force in X and Y direction. Okay, alright. So then here we have another example of the pipe with U shape. Pipe with U shape. Okay, the pipe here is the redirecting the water flow to 180 degree. Okay, for example, we have another example of pipe. So pipe here, looking like this in U shape. Okay, so our control volume here is just the pipe here, right? So the pipe here is our control volume, the area that we're interested to study. Okay, that is control volume. Okay, and then we have here point 1. We have here point 2. The water flowing from point 1 to point 2. The point 2 here is a P ATM. Okay. Alright, so here we have anchoring force. Okay, anchoring force is a must in order for the pipe to stay static, not moving. Alright, why? Okay, what is the total force involved here? So we have, from considering the force in X direction moving to the right is positive. So from the equation, F total force equal to m dot V2 minus V1. This is the linear momentum equation that you will always be using to solve the problem of anchoring force. Anchoring force. Anchoring force. So if you encounter a problem about anchoring force, use this equation. Okay. Okay, now, so let's list all the force involved in X direction. So we have FRX, moving to the right is positive, so FRX. So we have another one here, P2, moving in the opposite direction, the same direction of FRX, so plus. Here you PATM, so we just say here F2 here, we have here F1. Okay, from the F1 here is from P1 A1, from pressure here, P1, and we have here from pressure PATM equal to P2, just write as P2. Okay, right, so we have here F2 plus, since force 1 also moving to the right, so F1 equal to m dot, and we have velocity 1. So which velocity 1 here, moving to the right is positive, so velocity 1 is positive, moving to the right, so V1 here, V2 is here, moving to the right. Okay, right. So, we have velocity 2 here, velocity 2 here. Velocity 2 here is moving to the left. So this is moving to the left, since we're considering the right move positive, so minus V2 minus V1. So we get here, the equation here. Okay, this is the total force in X direction. Okay, right. So in Y direction, okay, in Y direction, considering the positive is the upward, we have FRY. So FRY. Do we have another force in Y direction? We doesn't have at point 1. So at point 1 here, we only have F1 here, moving in X direction only. And at point 2, we have F2, moving also in X direction only. No, since there are no angle, so just FRY only, equal to m dot. So do we have velocity at in Y direction? So we doesn't have any velocity in Y direction, since the velocity is moving in X direction only. Okay, in X direction only, so velocity is equal to 0. So if Ry equal to 0, we have here. Okay, and then let's look at another example. Here we have a water jet. We have here water jet. Okay, well, this diffuse from the nozzle. Okay, the dot here is your control volume, the area that you're interested in study. So at the outside of the the water jet is diffused to atmosphere, PATM. So we consider the pressure involved in this problem is equal to 0, since the diffused to the atmosphere. Okay, here we have doesn't have any pipe, since it's only a water jet, it's not a pipe. So it doesn't have anchoring force that hold the water jet. Okay, there is no, since we cannot hold water, we cannot touch water. Okay, so the anchoring force here is equal to 0, and no anchoring force here. Okay, right now we have a plate. Okay, and then we have another anchoring force from the plate. Okay, anchoring force is applied to the plate so that the plate is not moving lah. Okay, so stay static. And then we have force from the water equal to 0. Why 0? Because P ATM here. P ATM. Okay, alright, so now let's list all the force involved. So we have the water jet here. The jet diffused to atmosphere, and then we have here a plate. Okay, we have here a plate. We have a plate here. The plate is held by anchoring force of FR. FR anchoring force. Okay, we have water diffuse here. Okay, and this is our control volume. It's for control volume CV. So what else involves here? We have V1. So do we have V2? So here the jet is colliding with the plate. So when you collide to something, the velocity here is we consider equal to V2 equal to 0. The same as the Pitot tube. Okay, the same as the Pitot tube, because this incident area, accident area. Okay, so we have only V1, V2, FR. Okay, this is the only force involved. So let's consider the x direction moving to the right is positive. So we have FR moving to the left, so it's negative FR. Do we have another force? So since the water is diffused to atmosphere, so you consider P ATM equal to 0. So consider is. Let's just write it first. So F2 here from P ATM, F2. F2 is equal to P ATM times E2. Okay, since P ATM is equal to 0, so F2 is equal to 0. Equal to M dot. We have V1, V2 minus V1. But since V2 is equal to 0, so we only have M dot minus V1. That's left. This is just what left. Okay, and then in y direction, consider moving upward is positive. Do you have any force moving upward? No, it doesn't have any force moving upward. So FR y equal to 0. Very simple. Okay, alright. So that's all for today. So for your homework, please answer the question given in this video and submit your work today before 11:30 p.m. So this is your homework. The homework can be found in your slide notes. Okay, the notes I given you before in chapter 3. Okay, example force. This is example from example 10, question from example 10, and question from example 11. Also, question from example 12. You need to solve all of this question. You can refer the problems of the method I showed you before. Okay, in this example 1, example 2, example 3, to solve the problem of example 10, 11, and 12. Okay, well, that's all for today. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.